All right, so section 3.8. So this is derivatives of inverse functions. And they also say in logarithms. Okay, so what we need to know is we need to know the definition for the derivative of an inverse. And it comes from here, so theorem. Derivative rule for inverses. So if f has an interval domain I and f prime of x exists and is never zero on I, then its inverse is differentiable. At every point. So really this is just kind of talking about where it exists. So the value of the derivative of the inverse, so f inverse prime, at b in the domain of f inverse is the reciprocal of the value of f prime at the point A, which is equal to f inverse of b. Okay. Whew. So what we say here is that the derivative of the inverse at b is equal to 1 over f prime evaluated at the inverse of b. So we're going to be using this this rule to be able to find derivatives and find their value. So since b is every point, we're really just going to kind of simplify this kind of expression that I'm just going to write x's in those locations because that works for us. So our example is going to be this. We're going to use this inverse rule, but our example is going to be so given the function f of x is equal to x squared, and we're going to say on x greater than or equal to 0, because I want this function to be 1-to-1, so it's going to have an inverse on this particular domain. And its inverse, well, the inverse of x squared on positive x equals 0 is, so the inverse function is the square root of x. So what I want to do is I want to use this function to find the derivative of this function. Find the derivative of f inverse of x, which is equal to root x, using the derivative of an inverse rule. So what I'm going to do is I'm going to take the derivative. So the derivative of the inverse of x. So what I want to do is I want to find the derivative of this particular function is equal to 1 over f prime of f inverse of x. So this f is actually this function here. So in order to find the derivative of this root function, we're going to use this function here. So just kind of making a list of everything. What I know is that we know f inverse of x is equal to the square root of x. And I know that f prime of x, well, remember that I'm not talking about the derivative, we're talking about the f function. So f prime of x is going to be the derivative with respect to x of this x squared is going to be equal to 2x. So what we need in order to find this thing is we're going to need the derivative of the function and the inverse function. So that means back to this f inverse prime of x is equal to 1 over, well, f prime is this 2x. So this is 2 evaluated at this f inverse. So we're going to evaluate it at this f inverse of x. So what that means is that this function is going to be stuffed into this function. I'm going to be composing these functions. So this function is going to be composed into this function. So this is going to be 2 times, so right here's our x, this is going to be right over there, root x. Notice how the inverse function is getting stuffed into the derivative. So what we know is this is equal to 1 over 2 root x. And we can do a quick check because I'm choosing this one. I'm trying to verify this because we already know the derivative of this function. So if f inverse of x is equal to square root of x, which is the same thing as x to the 1/2, and then the derivative of this thing, the derivative of that particular function is going to be 1/2 x to the minus 1/2, which is going to be equal to 1 over 2 root x. So it does work. This rule is actually working for us. Now there's a couple examples, like the very beginning ones, they ask you to do this. So this is going to be a lot like the first couple of examples. So example, find the value of the inverse derivative. So let's let f of x equal x cubed minus 2. What I want to do is I want to find the derivative with respect to x of the inverse function. This is the same thing as saying f inverse prime of x, okay? So those two things represent the exact same thing. This is the derivative of the inverse. This is also the derivative of the inverse at x equals 6, which happens to be equal to f of 2. So what we need is these two numbers are going to become important, like the 6 and 2, and we need to know where they actually go, okay? So this is going to be without finding f inverse. All right, so what we know is that that the derivative with respect to x of f inverse, which is the same thing as the derivative of f inverse, those things represent the same thing, is going to be 1 over f prime of f inverse of x. So what I need is I need to know what f inverse is. Since we're only trying to find a value of a point, I don't have to find the inverse of it. I really just need to know that that this says if this is f prime of b, this is going to be b as well. So taking a look at this particular thing. So what we know is that that f of 2 is equal to 6. We have that expression right here. So that means f inverse of 6 would be equal to 2, because if you go from function to inverse, you're going to go right back to this thing. So when I'm evaluating this essentially says that a is equal to 2, and then b is equal to 6. going right back to our original definition. So what I know is that b is equal to 6, which is going to go into here. So that means this f inverse prime of 6 is going to be equal to 1 all over f prime of f inverse of 6. We know that f inverse of 6 is equal to 2, so this is 1 over f prime of 2. So I know that that f of x is equal to x cubed minus 2. So I know the derivative of this function is going to be 3x squared. So this is 3x squared, where x is 2. So this is going to be 1 over 12. So note, f prime of x is equal to 3x squared, right? So just plugging that in here evaluated at 2. So that means f prime of 2 is equal to 3 times 2 squared. That's where I got that from. Okay. So there's a couple examples in there that are asking me to do this. Really what I want you guys to really focus on is being able to find the derivative of the inverse function. So the very first example I find a lot more important. So why we need this. So what we're going to do is we're going to find the derivative of the natural log function. So the way we're going to do this is we're going to say we're going to talk about f of x and f inverse of x. So the natural log function I know is the inverse of e to the x. So what we know is note that if f of x is equal to e to the x, then the inverse function is going to be the natural log of x. So I'm going to be able to find the derivative of this thing using this. So what I know is that the derivative with respect to x of our natural log function is the same thing as the derivative with respect to x of f inverse, df inverse dx, which is the same thing as, I want to use that exact same notation, that's the derivative of the inverse function, which is going to be 1 over f prime of f inverse of x. So the derivative of the natural log function is going to be related to the derivative of f evaluated at this function right here, evaluated at this inverse. Well, what I know is I know that that if f of x is equal to e to the x, then f prime of x is also equal to e to the x. So this is going to be equal to 1 over, remember this is, what we're going to do is this function is going to get stuffed into here, right? Because this needs to be f prime of f inverse. So this is going to be e evaluated at that natural log of x. And you know e and natural log are inverse functions. So this, they essentially kind of cancel. So this is going to be 1 over x. So the derivative of the natural log function is 1 over x. So what this, what the derivative of the inverse rule actually gives us is allows us to, since we know the derivative of a bunch of functions, and we know how to find the inverse of all those functions, now we know how to find the derivative of the inverses of these functions. So as long as I know this function and its derivative, I can also find the derivative of the inverse function. And we're going to be using this to find the derivatives of the inverse trig functions in the next section. So here's our new rule. This is just going to be in our toolbox. We don't need to do this by hand. I need you to just know that the derivative of the natural log of x is 1 over x. If you have to prove it, you know how to do that. So what we say here is our theorem says the derivative with respect to x of the natural log of u is going to be equal to 1 over u times du dx, where u is some function of x. So what this is this is just the chain rule, that if u is a function of x, that the derivative of the natural log of something is going to be 1 over that something multiplied by the derivative of what's inside it. So a quick example would be, what is the determine the derivative If I have the natural log of x squared minus 5x plus 1. If I want to find the derivative of this thing. So this is y is equal to this. So if I want to find y prime, what I know is that that y prime is going to be the derivative of the natural log function. Notice how this x squared minus 5x, this x squared minus 5x plus 1 is the same thing as my u. So what I know is the derivative of the natural log of u is going to be 1 over this u multiplied by the derivative of u. So this is going to be equal to 1 over x squared minus 5x plus 1 multiplied by the derivative of the inside. So this is going to be equal to 2x minus 5. So we're done here. This is going to be equal to 2x minus 5 all over x squared minus 5x plus 1. B, what if y is equal to the natural log of the cosine of x? We have to do absolute value because natural logs are not defined for negative numbers. The domain of a natural log is 0 to infinity. So if I have y is equal to the natural log of x, if you look at its graph, it looks like this. So we know that the domain has to be x is greater than or equal to 0. So the reason why you'll always see absolute values in here, and it really should be in here as well, it's because it's not defined for negatives. Alright, so the derivative of the natural log of the cosine of x. Well, we know that y prime, well, we know that our u function is our cosine of x. So the derivative of the natural log of something is going to be 1 over that something. So the derivative, remember we're doing outside to inside. So the derivative of the natural log part is 1 over that cosine of x multiplied by the derivative of the cosine of x. The derivative of the cosine of x is minus the sine of x. So this is going to be equal to minus the sine of x over the cosine of x, which actually is the same thing as minus tangent of x. So the derivative of that natural log of the cosine is going to be minus the tangent. Now we can, we can continue to get more and more complicated. So if I have something like this, find the derivative of the following. F of x is equal to we'll do another easy one real fast. Natural log of 4x. So the 4x is inside the layer. So what I know is that f prime of x is going to be equal to 1 over that u, so 1 of that 4x multiplied by the derivative of 4x. So this is just going to be 1 over x. This is where we're going to get a little complicated. What about y is equal to x times the natural log of x all over 1 plus the natural log of x? Alright, so what we know is that, I know we ramped it up pretty quick. This has a bunch of rules in there. Like the numerator is a multiplication, and this is also a division. So when we have to take the derivative of this thing, we have to be a little bit careful. First, I know that the numerator is going to be f, and the denominator is going to be g. So when I want to do y prime, this is going to be equal to f prime g plus, my bad, f prime g minus f g prime all over g squared, because we're going to have to use the quotient rule. The problem is that f is a product. This is a product of two things. So we have to be a little bit careful here. So I'm going to do it a couple ways. We're just going to kind of talk about f and f prime. So if f is equal to x times the natural log of x, then we know that f prime of x is going to be equal to, well, since this is a product, So I have to say that, this is going to be u and v. So this is u prime v plus uv prime. So the derivative of the first times the second plus the first times the derivative of the second. So what this is going to be is the natural log of x plus 1. Now we know that if g is equal to 1 plus the natural log of x, then g prime is going to be the derivative of 1 is 0, the derivative of natural log is 1 over x. So now we can fill in the blanks up here. So that means y prime is going to be f prime g. So this is the natural log of x plus 1 times the g function, which is 1 plus the natural log of x, minus f, which is x times the natural log of x, times g prime, which is going to be 1 over x, all over the denominator square. So now we're going to clean things up. What I know is that this is all multiplication. These are all multiplications here, so that means this and this will cancel. This x does not cancel with the natural log of x of the argument of the natural log, because it's inside that function. That's composition, not multiplication. So be careful. Do not cancel that x. It wouldn't make sense just to write ln somewhere. So now what I'm going to do is I'm going to expand this thing completely and try to simplify this. Now, I know a lot of you guys are going to want to cancel one of these, but remember, if you cancel, you have to cancel from all three pieces, and unfortunately this term over here doesn't have a 1 plus natural log of x, so you cannot cancel. So what I'm going to do is I'm going to FOIL this numerator out. So natural log of x, natural log of x times natural log of x is going to be the natural log of x quantity squared. Inside is going to be 1, and the last is going to be the natural log of x. So what we're going to get is we're going to get natural log of x times 1 is natural log of x. Natural log of x times the natural log of x is going to be the natural log of x squared. 1 times 1 is 1, and 1 times the natural log of x is the natural log of x. Then we have minus this natural log of x all over 1 plus the natural log of x squared. What we can see is that these two will cancel here. So we're left with, I'll write it in descending order, natural log of x squared plus natural log of x plus 1 all over 1 plus the natural log of x squared. And that's it. What we can do is we can, we're taking the derivatives of things that have natural logs. We can use our natural log rules to simplify the expression before taking the derivative. So, remembering the rules of logs. So the very first one, natural log of a times b is equal to the natural log of a plus the natural log of b. The natural log of a divided by b is equal to the natural log of a minus the natural log of b. And then c, the natural log of a to the c power, so this, is equal to c times the natural log of a. So using those three rules, we can take derivatives much quicker. So an example would be determine the derivative. So A, if y is equal to the natural log of x squared times root x plus 1. Well, a couple ways you can do this. One way, you can just take the derivative as it sits, which becomes kind of messy, because you're going to take the we can show. I'm going to do it both ways. So I'm going to do it without using the rules, and I'm going to do it using the rules just to kind of show you how much quicker this is. So y prime, if I want to take the derivative of the natural log of something, this is my u. So it's going to be 1 over that u multiplied by the derivative of this thing. Now the derivative of this thing is a little complicated because, remember, the derivative of u. So what we're going to have is this is going to be an f and this is going to be a g, knowing that g is x plus 1 to the 1/2. So we know that this is going to be f prime g plus f g prime. So when I take the derivative of this is going to be the derivative of the first times the second plus the first times the derivative of the second, which is 1/2 x plus 1 to the minus 1/2 times the derivative of what's inside, which would be 1. So what we get here is 2x root x plus 1 plus x squared all over 2 root x plus 1 all over x squared times root x plus 1. And we could clean this up quite a bit, but yeah, might as well. Let's do it. Let's clean this up and maybe I can show that they're equal. Well, the first thing you'd have to do is you have to add these two fractions. So in order to add these two fractions, what I have to do is I'd have to multiply the top and denominator, numerator and denominator, by 2 root x plus 1. Now, I don't want to cancel anything. I just want to expand the numerators. So 2 times 2 is going to be equal to 4. And I'm going to have an x, and then root x plus 1 times root x plus 1 is just going to be equal to x plus 1. Plus x squared all over 2 root x plus 1. That's just adding these numerators, and I still have the denominator of x squared times root x plus 1. Now what I can do is I can multiply by the reciprocal, which really basically makes this denominator multiplied by that denominator. So this is going to be equal to, expanding this numerator, I'm going to have 4x squared plus 4 plus x squared. And then when I multiply these two denominators together, I'm going to have 2x squared times x plus 1. So we're going to have 5x squared plus 4 all over 2x squared times x plus 1, which is about as simple as I can get. Now there's a much better way, and we're going to use that from now on. So starting back again, the natural log of x squared times root x plus 1. Well, using the very first rule, that the natural log of a product is the sum of the sum of the logarithms. So I'm going to rewrite y before I take the derivative. This is the natural log of x squared plus the natural log of, I'm going to write this as x plus 1 to the 1/2. I also know that logarithm of a to a power of c, that means I can take the powers and turn them as coefficients. So this is 2 natural log of x plus 1/2 natural log of x plus 1. And that was really quick. Now when I take the derivative, oh my gosh, this is so much easier. So the derivative of this is going to be 2 times 1 over x, because that's the derivative of the natural log function. And this is going to be 1/2 times, well, the derivative of this is going to be 1 over x plus 1. So this is equal to 2 over x plus 1 over 2 times x plus 1. There's my mistake. Now, it can be shown, because this thing actually simplifies. I missed the x here. I missed that x there. So you can cancel an x from everything because all these have it. So I can factor an x on the top and I can cancel one on the bottom. So this is going to be 5x plus 4 all over 2x times x plus 1. And I'm not going to do it, but if you add these together, you'll get that. And see how much quicker this drew? Oh, my bad, I have a bunch of equalities. This is y, and the rest of these are y primes. But can you see the derivative of this to this? So much easier than that mess right there. And it can be done quickly. So expanding your logarithms using these rules make the job so much easier. B. So now that we know expanding the logarithm is a lot easier, we can do something like this. The natural log of 1 all over the square root of x times the square root of x plus 1. So I'm not doing the quotient rule mixed with the product rule. What I'm going to do is I'm going to rewrite this thing as the natural log of the division is going to be the natural log of the top minus the natural log of the bottom. Now the natural log of a product is the sum of the logarithms, so we have to be a little careful here. So natural log root x plus the natural log of root x plus 1, but there's an error here. And I know it's the same error that we keep bringing up. So remember that this is subtracting whatever we get here. So this needs to subtract whatever we get there, okay? So it's actually going to turn that into a minus sign. So natural log of 1 minus the natural log of x minus the natural log of root x plus 1. Now we can rewrite all these powers. Actually, if you check out the natural log of 1, the natural log of 1 is just 0. This is 0 minus the natural log of x to the 1/2 minus the natural log of x plus 1 to the 1/2. So the last thing we're going to do is pull out these powers. So minus 1/2 natural log of x minus 1/2 natural log of x plus 1. And remember, this is y. So that's just quick expansions. And if you get really good at it, going from this line to this line can happen in one step. You don't really need to write all that. I'm just going to verify it. So y prime is going to be the derivative. Well, minus 1/2, because it's a constant, so the derivative of the natural log of x is 1 over x. Again, pull out the constant and take the derivative of this is going to be multiplied by 1 over x plus 1 times the derivative of x plus 1, which would be 1. So this is going to be minus 1 over 2x minus 1 over 2 times x plus 1. That's y prime. Okay, so another thing that this can help us do is, this is called logarithmic differentiation, is example, using what I'm going to say is I'm going to have y is going to be equal to, start kind of easy here. So let's say 2x times the square root of x plus 1. So what I'm going to do is I know in order to take the derivative of this, you know, this is a product, so I'd have to use the product rule. So this is f times g. So what I'm going to do is I'm going to natural log both sides. So I'm going to natural log this side, and I'm going to natural log this side. So what we have here is, oh my gosh, stop. I apologize for the over noise, but it's crazy time right now. All right, I'm gonna pick this up with the second video.